Hello, Leiden geometry students. In this assignment, we are going to talk about special right triangles. In particular, we're going to talk about Pythagorean triples, and then the 45-45-90 triangle, and the 30-60-90 triangle. Now, what these are just patterns that show up all the time when we're dealing with the Pythagorean theorem and then later trigonometry. And what I mean by that is, I'm going to give you a set of problems here. Here are 4 right triangle Pythagorean theorem problems, and you're going to use Pythagorean theorem to find x. However, there's a big shortcut. By the time you get to the last problem, you shouldn't have to do any work. You should be able to look at it and just go, oh, I know what the answer is going to be. And the pattern has to do with the numbers here. You'll notice that the numbers are being repeated. In the first right triangle, the 2 legs are 3 and 4. You're looking for the hypotenuse. In the second triangle, it's 30 and 40, looking for the hypotenuse. In the third triangle, it's 300 and 400 for the legs. You're looking for the hypotenuse. And in the last one, 3,000 and 4,000 for the legs. You're looking for the hypotenuse. So there's obviously something going on with the numbers here. All right, so if we took this first one, if we were going to solve this by the Pythagorean theorem, we'd say 3 squared plus 4 squared and take the square root. Looks like this. Well, 3 squared is 9, 4 squared is 16. Add them up, we get 25. And when we take the square root, it's going to turn out to be 5. When we use do the Pythagorean theorem with the legs 3 and 4, we get 5 for the hypotenuse. In the second problem, we're going to do the same thing with our legs, 30 and 40. Square them, add them, take the square root. If you do that, it turns out to be 50. And right off the bat, you should notice a pattern of these numbers. 3, 4, 5 works. 30, 40, 50 becomes the hypotenuse. What about hundreds? If we do 300 plus 400, if we square them, add them, and take the square root, what are we going to get? Well, you should get 500. So this last problem, we got legs of 3,000, 4,000. What's the hypotenuse going to be? If need be, take out a calculator and do it by the Pythagorean theorem. However, based on the pattern of what you see before, you might just be able to guess the answer. If you do 3,000 squared plus 4,000 squared and take the square root, you do get 5,000. See, here's what's going on. If you randomly pick 2 numbers to put into the Pythagorean theorem, like you're going to square 2 numbers, add them, and take the square root, and you just randomly stick a number in for each of these things, if you do this 99.999% of the time, you're going to end up getting a decimal for your answer. And here, just for example, here, I would do it with a 4 and a 7. 4 squared plus 7 squared, take the square root, we get a decimal. 11 squared plus 13 squared, take the square root, we get a decimal. If you randomly pick 2 numbers, you can try this. Take 2 numbers, not the ones in the last page here, but take 2 numbers, square them, add them, and take the square root, you basically get a decimal. There's only a few, relatively, exceptions to this, and one of them are the numbers 3 squared and 4 squared. If you do 3 squared plus 4 squared and take the square root, it comes out to 5. But, as we saw in the examples before, it's not just 3 squared and 4 squared. If you do 3 squared plus 4 squared, we get 5. But any multiple of 3 and 4 will give us the same multiple of 5. In other words, if I take both these numbers as we did a few problems ago and I multiply them, the 30 and the 4 by 10, our result is going to be the 5 times 10. So if we did 30 and 40, 30 squared plus 40 squared and take the square root, we get 50. But in those problems, we just multiplied by 10 and 100 and 1,000. You could multiply by anything. Let's say we take the 3 and 4 and multiply them by 2. If you do 6 squared plus 8 squared and take the square root, you'll get 10. If we multiplied them by 3, you'd have 9 squared plus 12 squared. And when you take the square root, you get 15. That's 3 times 3, 4 times 3, 5 times 3. Whatever the number is. Here, we move into decimals. This is multiplying by 1/10. 1/10 times 3, 1/10 times 4 gives us 1/10 times 5. Any multiples of the numbers 3, 4, and 5 are going to work in the Pythagorean theorem as long as the 5 is the hypotenuse and you multiply them all by the same thing. So for example, a problem might be like this. If I gave you the sides of a triangle and I told you the 2 legs are 15 and 20, you might be able to spot that this is 3 times 5, this is 4 times 5, so the hypotenuse should be 5 times 5, which is 25. Another example, take all 3 of the numbers, multiply them by the same thing, and it'll work again. This is 3 times 7, and this is 4 times 7. So what will the hypotenuse be? It's 5 times 7, or 35. So the numbers 3, 4, 5, and any multiple of those 3 numbers will work in the Pythagorean theorem. Those numbers are called the Pythagorean triple, as it says on the top of the screen. Now, we aren't always looking for the hypotenuse. We could be looking for a leg. Here, we're looking for the left side, the x over here, but the same rule still works. But the trick is you have to be able to spot it. You have to look at this and be like, oh, wait a minute, that's a 3, 4, 5 triangle. And that's the tricky part here. Because if you look at the 6, you go, oh, wait a minute, that's 3 times 2. And this 10, oh, that's 5 times 2. So shouldn't this other side be 4 times 2? So it's a 3, 4, 5? Yes, it is. If you do the Pythagorean theorem, 10 squared minus 6 squared, and take the square root, you'll get 8. Same thing over here. If the left side here, the 44, ooh, that's 4 times 11, and the hypotenuse is 5 times 11, what will the missing side be? You can use the shortcut or do the Pythagorean theorem, 55 squared minus 44 squared. And if you do that, you're going to get 33 times 11, which will be 33. So 3 times 11, 4 times 11, and 5 times 11 work in the Pythagorean theorem. These numbers, once again, are called Pythagorean triples. And it's not just 3, 4, 5 that work. In fact, there's technically an infinite number of Pythagorean triples. You can go to Wikipedia and just type that in to see them. And here's a whole bunch of them. These are the small ones with numbers less than 100. And here's the next ones with numbers less than 300. And if you're looking at this going, oh, man, don't think I have to remember that, do you? No, you don't have to remember that unless you really think this is super awesome and want to. However, it's a shortcut that's supposed to be able to help you sometimes. See, if we had to solve this problem, these problems without the shortcut, it might take a while. But if you can recognize that the 3, 4, 5s, you can just go straight to writing the answer. So all of these sets of numbers work in the Pythagorean theorem. It's probably unrealistic for most of us to remember all of them. However, some of them come up more often than not. For example, it is worthwhile for everybody to remember the 3, 4, 5. And then here's another little hint here. Your teacher, your geometry teacher, probably only remembers these. Every time they're writing a test or a quiz and they need a Pythagorean theorem problem, they're just going to take one of these sets of numbers and multiply everything by 2 or multiply everything by 5 or by 10. And so you could jump straight to the answers with these. Most people don't remember the other ones, maybe a few exceptions in there. So for you, you probably don't want to try to learn all of these. You might wish to learn all 4 of them. You definitely want to know this one of them. It comes up often enough that it's worth remembering. It will save you a bunch of time. Okay, next we're going to talk about the other shortcut special triangles. And the other ones have to do with a mix of Pythagorean theorem and something called trigonometry, which we'll get to later in the year. And the 2 other shortcut triangles are called the 45, 45, 90 and 30, 60, 90. These are not Pythagorean triples. These do not work in the Pythagorean theorem. They're totally different, but they do have something to do with the Pythagorean theorem. Let's start with the first one, 45, 45, 90, because it's easier. First, let me show you the 45, 45, 90 triangle. It looks like this. We're talking about Pythagorean theorem, so it has to be a right triangle. And what's special about this right triangle is its isosceles. These 2 sides are going to be the same as each other. It's a right isosceles triangle. Every right isosceles triangle will have this same shortcut. Since it's isosceles, those 2 sides the same means these 2 angles are also the same. And if those angles are the same, and the 3 angles have to add to 180, well, the only set of numbers that work are 45, 45, and 90. So this is the 45, 45, 90 triangle. Why has this come up often? Actually, it comes up in a whole bunch of ways, but probably the easiest one to understand is this picture. This is a square. You got a right angle and 4 sides, and all the sides are the same length. Well, if we look at the length of the diagonal here across the middle, what we've just done is created a 45, 45, 90 triangle. This is an isosceles right triangle, the diagonal in a square being the hypotenuse. So let's take a look at the numbers that actually show up when we use the 45, 45, 90 triangle. Here, if we asked you to do the Pythagorean theorem to find x, you'd have to set this up and say 5 squared plus 5 squared is equal to x squared. 5 squared plus 5 squared, then take the square root. What's going to end up happening is you're going to have the square root of 50. Now, you can turn that into a decimal. It's like 7.1. Or if you break down the square root, what will happen is you'll end up getting, since the first thing that happens, it breaks down to 25 times 2, you end up getting 5 square root of 2. Now, that's significant. Our sides were, the legs were 5 and 5. The hypotenuse was 5 square root of 2. This happens, we get the kind of the same numbers for all of them, except the hypotenuse has an extra root 2 on it. This happens because we have the same number for 2 of the sides when we use the Pythagorean theorem. We try a couple other ones. If we have 3 and 3 for the legs, and we'll look for the hypotenuse, you do 3 squared plus 3 squared and take the square root, it'll turn out to be 3 square root of 2. So our legs are 3 and 3, the hypotenuse is 3 root 2. And problem number 3, if you do the Pythagorean theorem with the legs being 2 and 2, you're going to do 2 squared plus 2 squared and take the square root. And again, you get 2 square root of 2. This always happens when your 2 legs are the same. If our 2 legs are 3 and 3, the hypotenuse is 3 root 2. In the last problem, the 2 legs are 5 and 5, the hypotenuse is 5 root 2. In problem number 4, the 2 legs are 7 and 7, what's the hypotenuse going to be? It'll end up being 7 root 2. It's always going to be the same number with square root of 2 tacked onto the end. which is why we kind of represent this with letters. We can say if I have a right triangle here, and it's isosceles because two of the sides are the same, I got my sides as G and G. The hypotenuse, it doesn't matter what G is, it could be 7 or 48 or 31.9, but the hypotenuse is going to be that same number with the square root of 2 tagged on to the end. So the key to using a 45, 45, 90 triangle is to recognize it. Here there are 4 problems up on the screen. 3 out of the 4 are 45, 45, 90 triangles. 3 of them follow the pattern. Which is the only one that doesn't follow the pattern of a 45, 45, 90? It's letter C, because our 2 legs aren't the same. In the first one, 6 and 6, the hypotenuse will be 6 root 2. 10 and 10, the hypotenuse is 10 root 2. But in letter C, I have 2 different numbers for the legs, so this is the one that isn't going to follow the pattern. Okay, so here are 4 quick problems. Let's just do the first ones here. For number 7, 8, and 9, find x. Number 7, it's 10 root 2, 10, 10, 10 root 2. And number 8, we've got a leg in the hypotenuse, but it's following the pattern, so we can figure out the other side is just going to be 7. And number 9, we got the 2 legs are 5 and 5, so the hypotenuse is going to be 5 root 2. The last one, we only have the hypotenuse, but we know the 2 legs are the same, so it's still going to follow the pattern. They got to be the same thing. So if the hypotenuse is 4 root 2, then each of the legs will have to be what? Each of the legs will have to be 4. Good. So that's the 45, 45, 90 triangle. We represent that using a picture looking something like this. And it doesn't matter what letter we're using here. But the idea here is if you can spot it, if you see this in a problem, you don't have to do the work. You recognize the pattern, you can jump straight to writing down the answer. There's another triangle that also does the same thing, but it's not as easy. It's a little bit more complicated than this. And that other triangle is called the 30, 60, 90 triangle. I'm not going to spend the time showing you where it comes from here, but this is what you end up with. We have a 30, 60, 90 triangle. That means we have a 30-degree angle, check right there, a 60-degree angle, and a 90-degree angle. And then we always have this pattern. We have one of the legs is A, some number, and the hypotenuse is twice of that. Then the other leg is going to be that same number with square root of 3 on the end. Usually to do this, people keep an example of this picture right next to them while they're doing the problems. For example, here's the question on the left. We're trying to find x and y. It's a 30, 60, 90 triangle because this angle's 90, this angle's 60. If we subtract them from 180, this last angle will be 30. So I'd go and look at my notes if I don't have it memorized. This is what the 30, 60, 90 triangle is supposed to look like. And we're just going to match up which sides are supposed to go with which. So if we look here, this 2a is the hypotenuse. That's in the same spot as the 10, the hypotenuse. So these two are going to go together. So I'm just going to say 10 is equal to 2a. Let me do that for all 3 sides. I can also match the a root 3, the longer leg here, is in the same spot as the x, the longer leg. It's also between the 90 and the 30. That's how some people recognize it, between the 90 and the 30. So this x is going to be a root 3. And then the short leg between the 60 and the 90 is the a, and the other triangle here, that's the y. So I'm going to just set those equal to each other as well. Now, if you do something like this, one of these equations is going to be something you can solve. And in our case, it's this one. 2a is equal to 10. If 2 times a equals 10, we can figure out what a is. 2 times what is 10? Oh, it's 5. A is 5. Once you've solved one of them, you can just plug it in to know the other sides. If a is 5, then this side is just a, so this side down here is going to be 5. And this side is a root 3, so that's just going to be 5 root 3. And that's it. We got the measures of all 3 sides without doing too much work. The trick is being able to pair up the sides together. Let's try that again. Keeping the same example triangle over here on the right, let's just pair up the sides. Starting here, the 2a, the hypotenuse, it's a u there. It might be a little hard to read, but the 2a is a u, so we'll set those equal to each other. And then the a, that's the short side between the 60 and the 90, that's the same as the 8, so I'm going to say 8 is equal to a. And then this side here on the bottom, the long leg, is the a root 3, so we'll set it equal to a root 3. Now, one of these equations we can use to solve for a, and it's the easiest one possible. It just says a is 8. So all we got to do is plug 8 in for a in these. If if a is 8, then 2a is going to be 16, and a root 3 is going to be 8 square root of 3. And that's it. That's the whole problem. One more. All right, so we have another problem. In this case, we have the 10 root 3 here, and the one with the root 3, it's going to match up with the other one. But first, again, you got to match up the sides. A root 3 is the same as 10 root 3. I'm going to set them equal to each other, but you might be like, hey, do I even have to write that? Doesn't that just tell me A is 10? Yep, it does. And if you can recognize that right off the bat, it means you're doing well with this. But I'm going to keep going. So 10 root 3 is A root 3. A is in the same spot as this b, so I'm going to make this side into a. And the 2a is the hypotenuse, so I'm going to put the 2a over here. So we have to take one of these equations and figure out what a is, and in this case, it's this one up here. If 10 root 3 is a root 3, then a is 10. So this side over here on the right, the short leg is just going to be 10, and this side, the hypotenuse, is just going to be double that. It'll be 20.